Section 1.5, Inverse Functions and Logarithms. A function is a one-to-one function if it never takes on the same value twice. That is, if we have different x values, then we get different y values. In order to see if a function is one-to-one, we have a test that's analogous to our vertical line test called the horizontal line test. It says that a function is one-to-one if and only if no horizontal line intersects its graph more than once. So let's look at some examples. Is the function f of x equals x cubed one-to-one? Well, if f of x equals x cubed, we have x1, and it's different than another x value, x2, then that means that x1 cubed will have to be different than x2 cubed because no two different numbers have the same cube. So that tells us that f is one-to-one. We can also see this by using our horizontal line test. If we draw the graph, let's see. All right, pretty bad. So we've got y equals x cubed. If we draw any horizontal line, let's say this one, see I only touch it over there. If I draw this horizontal line, I only touch it over there. And you could try drawing infinite lines and see that you'll only ever touch the graph once. Or in other words, you will not be able to find a single line that touches it twice. Let's look at the next example. Is the function g of x equals x squared one-to-one? Well, in order to break this thing and see that it's not one-to-one, all we have to do is find a single y value that's duplicated. So in this case, if we plug in 1, we look at g of 1, then 1 squared is 1. But minus 1 squared is also 1, so g of minus 1 is a second y value that is equal to our first y value. Rather, there's two different x values, 1 and minus 1, that give us the same y value of 1. So g is not one-to-one. We can also see this using our horizontal line test. It's a little bit easier to see that a function is not one-to-one. You only have to find a single horizontal line that breaks things. We could just draw one right here. There we go, and this one hits it twice. Tells you immediately this is not one-to-one. Y equals x squared. Okay, so if f is a one-to-one function with domain A and range B, then its inverse function, f inverse, has domain B and range A and is defined by f inverse of y equals x if and only if f of x equals y. So the inverse basically just takes you backwards. Originally, for functions, we plug in an x value, we get a y value. For an inverse, we plug in a y value, and we get back the x value that would have gotten us that y value. So let's do an example. If f of 1 equals 5, f of 3 equals 7, and f of 8 equals minus 10, let's find f inverse of 7, f inverse of 5, and f inverse of minus 10. So let's look at f inverse of 7. Well, we know f of 3 is 7, so f inverse of 7 must equal 3 because f of 3 equals 7. 3 is the x value that gives us the y value of 7, so f inverse of 7 takes us from y and returns the x value. Similarly, f inverse of 5 will have to equal 1 because f of 1 equals 5. And lastly, f inverse of 10 has to equal 8 because f of 8 is minus 10. Oops, wait, minus 10. F inverse of minus 10. Okay, the letter x is traditionally used as the independent variable. So when we concentrate on f inverse, we usually reverse the roles of x and y to get f inverse of x equals y if and only if f of y equals x. So this can be a little bit confusing, but the idea is that when we have a function, we plug in an x value, we get out a y value. When we use the inverse, we look at y values and we get back x values. However, if we look at the inverse itself as a function, then when we like to talk about functions, we like to always talk about things we're putting into the function, so we like to talk about x values. So we kind of relabel the y values that we look at for the inverse function that give us back the x values, and we just call those y values x values also. We try to make this as confusing as possible for you guys. So this means that in general, if we look at a function f of x, it equals some y value. If we look at a function f inverse of x, this x value we're plugging in is actually the y value for the function that it's inverting. We just relabeled it x again, just so we could keep using x and plug it into our f, even though it's f inverse now. So then the y value that this returns is this x value. Okay, so by substituting for x and y, we get the following cancellation equations. This means that if we take f and then we take f inverse of f, then it returns the x that we started with. So it's kind of like we go from x to y, but then we go back from y to x. So it makes sense that you should return all the way back to x. Similarly, if first you go from f inverse, so first we go this way, and then we go this way, then we still get back exactly where we started, wherever it was. So either way, if we do f inverse of f, we get x. If we do f of f inverse, we get f. Let's find the inverse function of f of x when f of x equals x cubed plus 2. So first, let's start with y equals x cubed plus 2. Then let's solve for x. So if we move y to the other side and x to the other side, actually let's just subtract 2 from both sides, that's easier. So if we subtract 2 from both sides and move x to the left, we get x cubed equals y minus 2. So when we take the cube root, we get x equals the cube root of y minus 2. Okay, so like we said before, when we are talking about the inverse function, we usually like to plug in x, so we like to relabel things. So we're just going to relabel x and y right now. X becomes y, y becomes x. So our inverse function is f inverse of x instead of y, and that equals the cube root of x minus 2. And you can test that the cancellation equations will work. If we plug in x cubed plus 2 in over here for x, then we get x cubed plus 2 minus 2 is just x cubed, and then the cube root of that is just x. So it does return whatever you started with, and it works the other way too, you can test. Okay, so now let's talk about the graph of f inverse. The graph of f inverse is obtained by a reflection of the graph of f about the line y equals x. So when we reflect diagonally, we actually get our inverse function. So as an example, let's sketch these graphs. We want to graph f of x equals square root of minus 1 minus x. So how about we write f of x equals y. So then y equals square root of minus 1 minus x. So then y squared equals minus 1 minus x. So that implies that if we solve for x, we get x equals minus y squared minus 1. So if it was x equals plus y squared, that would just be a horizontal parabola. It's minus y squared, so we're going to flip it upside down, and then we're going to move it back 1. However, we only have the positive square root because of our original function. So this is only going to be defined for the positive part of the parabola. So we're going to start over here. The negative part would have been this part, but we're not going to include that. We're only including the positive part. And this is at minus 1, 0. We have to move it down 1 because of our minus 1. So this is y equals f of x. Now we want to reflect this thing. So we want to try to see if I can use another color. How about this one? Let's reflect over the line y equals x, which is this diagonal line. And let's see if we can draw our inverse function now. So minus 1, 0 becomes 0 minus 1 when I flip it over this line. And it should look something like that. Oops, not like that. Like that. That should be y equals f inverse of x. Okay, so let's see if that makes sense. Well, we already solved for x, so if we replace x and y, we should get f inverse of x is equal to minus x squared minus 1, which is exactly what this guy looks like over here. So, oh, and also remember that x has to be greater than or equal to 0. Okay, let's talk about our logarithmic function now. The logarithmic function with base b, denoted by log base b, is the inverse function of the exponential function f of x equals b to the x, assuming that b is positive and b is not equal to 1. So we write log base b of x is equal to y if and only if b to the y equals x. So this is how we translate back and forth between logarithmic functions and exponential functions. So because this thing is the inverse function, we end up with some cancellation equations. The log base b of b to the x cancels with b and returns just x. And similarly, b to the log base b of x is equal to x. We have a couple of laws of logarithms just like our laws of exponents. Log base b of a product is equal to the sum of the logs, kind of like how if we had the sum of exponents, that was a product of powers. So all of these laws of logarithms are basically just the laws of exponents in reverse. So the log base b of a quotient is the difference. The log base b of a power allows you to take that exponent and just put it right in front. Okay, let's use the laws of logarithms to evaluate log base 2 of 80 minus log base 2 of 5. So the log base 2 of 80 minus the log base 2 of 5 is equal to the log base 2. Well, this is subtraction, so we're going to use law number 2. So that's 80 divided by 5, if we want to write this as 1 log. Well, 80 divided by 5 is 16. So we want, let's see if we go back up. We know that log base b of x is b, it can be translated as b to the y equals x. So that means that it equals y, where y is exponent of b. So we're looking for the exponent that gives us 16. The exponent we have to put on 2 to get to 16. So in other words, 2 to something is 16. Well, 2 to 4 is 16. Okay, let's talk about the natural logarithm. The logarithm with base e is called the natural logarithm and is denoted by ln of x. So this is just a fancy way of saying take a log and put base e. Remember, e is about 2.7 something. So let's find x if ln x is 5. Well, this is just saying the log base e of x is 5. So if we translate using our equation, we just get e to the 5th is equal to x. Alternatively, we could use our cancellation equations for another solution. If we take e to both sides of this equation, e to the ln x, and e to the 5th, we just make both sides of the equations into the exponent. Then e to the ln cancels, we get x equals e to the 5th. Okay, let's solve the equation e to the 5 minus 3x equals 10. Well, we could take the natural log of both sides, ln of e to the 5 minus 3x, and that'll have to equal the natural log of the other side. Then ln of e cancels, so we get 5 minus 3x is equal to ln 10, which means that 3x is equal to 5 minus ln 10. And that means we can multiply by 1/3 to get x is 1/3 of 5 minus ln 10. And we can use the calculator to see that that's approximately 0.8991. Let's express ln a plus half ln b as a single logarithm. Well, ln a plus half ln b is equal to ln of a plus ln of b to the 1/2 power. By one of our laws of logarithms, we can just take anything multiplying by a log and make it into the exponent. So that's ln of a plus ln of square root of b, because that's what our half powers mean. And then this is a sum of logs, so we can write it as a single log using a product. So this is ln of a rad b. Next up is our change of base formula. For any positive number b, as long as b is not equal to 1, we have that the log base b of x is equal to ln of x divided by ln of b. This works actually for any base, not just e, and the proof is pretty much exactly the same. It's not so hard to prove, though. We can let y equal log base b of x. So then, by definition, we have b to the y is equal to x. We can then take the natural log of both sides and move the y out in front when we take the natural log. So we get y ln b is equal to ln of x. And then just divide both sides by ln of b. Because b is not equal to 1, ln b must not be equal to 0. Okay, so now we have a change of base formula. This means that we can use a calculator, because calculators often don't have different bases that you can put in, but they almost always have an ln button if it's a scientific calculator. So we can evaluate log base 8 of 5 by writing log base 8 of 5 is equal to ln of 5 over ln 8. And now we don't have to plug in any log base 8s into our calculator. We can just plug in ln 5 and ln of 8. Using our handy dandy calculator emulator, we can just do ln 5 divided by ln of 8. Okay, so we want this to 6 decimal places. So it looks like it's about 0.773976. Okay, let's sketch the graph of a logarithmic function. Well, our original ln function looks something like this, where ln of 1 is 0 because we need a 0 exponent to get to 1. And then the logarithmic function keeps growing, because our exponents need to be bigger in order to get bigger bases. And it gets smaller and smaller as we get closer and closer to 0. For the same reason that our exponential function could never get below 0, our logarithmic function can never get below 0 for the x value. So this is our original function, y equals ln x. Let's try to manipulate this in order to get y equals ln of x minus 2 minus 1. So first what we can do is we can move this thing to the right 2 units. That's what x minus 2 gives us. So this line that can never go past is the y-axis. that's also going to move over 2 units. So that's going to move over 1, 2. So that's like over here. That's x equals 2. And that means that this is the point, this was the point 1, 0. So this is going to be the point 3, 0. Let me get something like that. So that's y equals ln of x minus 2. And then all we have to do now is subtract 1. So we have to just move it down 1. Okay, let's put back our line. I draw it dotted because it's not actually part of our function, but it's a good indicator of where to draw this thing. So our point 3, 0 becomes 3 minus 1. And this is y equals ln of x minus 2 minus 1. Okay, let's talk about some inverse trig functions now. The inverse sine function, also called the arcsine function, is denoted by sine inverse, and it's also denoted by arcsine. It's the inverse of the sine function on the restricted domain. Remember that if you graph sine, it looks something like that, and it fails the horizontal line test repeatedly. However, if we restrict it, and we only go from minus pi over 2 to pi over 2, let's see, sine of pi over 2 is 1, so that's this restriction right over here, then it passes the horizontal line test, so it works. By restricting functions, we can often find inverse functions for them. So we restrict sine, we find an inverse just for this part, and we denote that by sine inverse. Okay, let's evaluate sine inverse of a half and tangent of arcsine of a third. By the way, cancellation equations tell us if we take sine inverse of sine or sine of sine inverse, then they'll cancel and return x just like we'd want. Okay, so we want to find sine inverse of a half, so we want to find the angle that gives us a half. So let's draw a unit circle. Okay. Sine, we're only looking at minus pi over 2 to pi over 2, so only looking at half the circle. We're looking for where the sine value is a half, so that's the first 30, 60, 90 triangle. So that means it's at angle 30, so that's pi over 6. So sine of pi over 6 is a half, so that means that sine inverse of a half is pi over 6. There could have been other values for the function if we had not restricted the domain to minus pi over 2 to pi over 2. Let's look at b now. How about we let theta equal arcsine of a third, and then we look at what the tangent of theta would be. This should make things a little bit easier when we can draw a triangle. Sine of theta would therefore be 1/3 by our cancellation equations, if you like. Okay, so let's see, let's draw a triangle. We have theta. We know the sine of theta is opposite of our hypotenuse, so that's 1/3. Okay, let's see if we can figure out what that last side of the triangle is. By Pythagorean theorem, that's b, and then that's 1, so b squared plus 1 squared is 3 squared. So solving for b, we get that b would have to be the square root of 9 minus 1. Square root of 3 squared minus 1 squared, because 3 is the hypotenuse. So that's 2 radical 2. Okay, so that means that the tangent of arcsine of 1/3 is equal to tangent of theta, which is opposite over adjacent. We said that this is 2 radical 2, so it'll be 1 over 2 radical 2. Next up, we have the inverse cosine function. Inverse cosine function, or arc cosine function, is denoted by cosine inverse, and it's on the restricted domain 0 to pi. Remember, we have to use a slightly different restricted domain for cosine because cosine looks like this. It's a phase shift of sine. So if we did the same exact restriction, we would have some duplicate, like it would fail the horizontal line test. So instead, we shift our restriction, and then we pass the horizontal line test. Okay, inverse tangent function, or arctangent function, denoted by tan inverse, is the inverse of the tangent function on the restricted domain from minus pi over 2 to pi over 2. Again, it should make sense if we draw some nice tangents. If we were to keep going past pi over 2, we would fail the horizontal line test. So we just stop drawing tangents once we get to pi over 2. And we just stop drawing once we get to minus pi over 2. We get a single one of these guys, and then it passes our horizontal line test. Let's simplify the expression cosine of tan inverse of x. We've got 2 different ways we could do this. How about we let y equal tan inverse of x? That tells us that tangent of y is equal to x, as long as we are from minus pi over 2 to pi over 2. Okay, we know that we can do something with the tangent of x in relation to secant of x. It's kind of hard to go from tangent to cosine, but we do have an identity that goes from tangent to secant. We know that secant squared of y is equal to 1 plus tangent squared of y. We could prove that if we know that sine squared plus cosine squared is 1. Okay, so this is 1 plus x squared. By taking square roots, we get that the secant of y is equal to the square root of 1 plus x squared, which we can do because the secant is positive when we're in the values from minus pi over 2 to pi over 2. So that means if we want to take the cosine of tan inverse of x, we're taking the cosine of y, and that's 1 over the secant of y. So it's just 1 over square root of 1 plus x squared. Alternatively, we can do it similarly to the way we did before and just draw a triangle. Again, let y equal tan inverse of x. Instead of theta, we can just keep using y. Doesn't really matter. We get, again, that tangent of y is equal to x. So if the tangent of y is equal to x, let's see what this triangle looks like. We get our angle is y. Tangent is opposite over adjacent, so that's x over 1. So it's x over 1. By the Pythagorean theorem, we've got x squared plus 1 squared is c squared. So the square root of 1 plus x squared must be c. So now we can take the cosine of tan inverse of x. That's just the cosine of y. Cosine is so that's adjacent over hypotenuse. So that's 1 over square root of 1 plus x squared, exactly as we got the other method. All right, last but not least, we have a couple of other inverse trigonometric functions for cosecant squared, for cosecant inverse, secant inverse, and cotangent inverse. And they're pretty much exactly what you would expect. They're functions that return the y value for cosecant y equals x, the y value for secant y equals x, and the y value for cotangent y equals x, assuming that you restrict their domains accordingly.